Okay. Let's pay attention. We are moving on to the main exercise for today. So what we are going to essentially do is, let me just do a turntable first. So what we're going to do next is we're going to see a really long workflow. I'm not sure how much we'll be able to cover today since we started off a little late. Let's see how much we are done until 9:30, and then we'll see if extending the session makes sense or maybe extending it a little later or earlier tomorrow makes sense. So we'll see it at that point. But the workflow that we're going to see is we're going to see how to create a skyscraper from scratch in Grasshopper. So all that we are going to take is this curve that you see floating around. That is the initial flow plate I have drafted in Rhino. And I took the flow plate from Rhino to Grasshopper, created the form of the entire tower. After I did the shape of the tower, that is the form of the tower, I added some details, which is the exposed flow plates and also some surface that is been removed off to see the flow plates in here. And after doing the detail, the next thing we'll do is extract the flow plates individually in Rhino drawing so that you can do it or you can use later for detailing the flow plates. And finally, towards the end, we will have a workflow where the skyscraper is analyzed for the amount of radiation that's going to hit the surface. And based on the radiation, we will work on a facade pattern. So this is the elaborate workflow we are planning to have. We'll break it down into small portions of teaching and then practice. Now, the first portion is where we are going to create the surface of the tower. Till now, when we use Grasshopper, that is until the previous class, we use Grasshopper more like a detailing tool. Like you're done with some basic elements in Rhino, you take it from the Rhino like the surface or something. And the surface is then divided into panels and you create a pattern. So only the detailing aspect is something we are doing parametric. In this example, from the very first step of how the surface of the tower is formed is created in Grasshopper, which means the advantage is there is going to be n number of options involved in how the surface itself is being created. And out of all the options, you get to choose what is the best form for the tower. And again, after that, you start adding details. And those details, you will again have a lot of options. You can see what is the best out of that, and so on and so forth like that. So basically, every single step in your design is going to be mostly parametric. What I'm going to do right now is I'm going to show you how I have imported this curve into Grasshopper to create this tower. I want you guys to guess and tell me what might be the steps involved in the algorithm for that. Okay, so the first step is the form. And as soon as I import the curve, so this is the algorithm, I right click, set one curve and select the curve. As soon as I import the curve into the algorithm, the surface of the tower is done. I'll show you what are the parameters I can change in this tower. Based on that, I want you guys to kind of guess what might be the steps involved in creating this specific algorithm. So first thing that we can change is the height of the tower. I can reduce or increase the height of this tower. That's the very first thing. Second thing is the form. I have a graph mapper that controls the shape of the tower into something different. You can always change the graph mapper to something different entirely. And again, play with the nodes to create a new tower. So let's maybe have this on top, have this at the bottom, and it creates something like this, right? And finally, the third parameter that I can change is the amount of twist. Just a second, let me disable the derailing step here. I think it's causing a lag. Yeah. So the next thing we can change is the amount of twist. I can kind of focus the entire twist to the bottom, or I can have it more evenly distributed like this. Or what I can do is I can again push it entirely to the top. I can just play on how the twist is happening. So I'll repeat the steps once again. Once I import the curve, there are three things I can change. First thing being the height of the tower. I can increase or reduce it. Second thing is a graph mapper that controls the shape of the tower. I can change it to something entirely different, either by changing the nodes or the graph itself. And finally, I can change how the twist is happening for the tower. I can push it entirely to the bottom, or I can have it more evenly distributed all around the tower like this. So, what are the steps that you think is involved in creating this tower? This is where we start, and this is where we finish. Just a random guess. So, this is where we start. We saw the things that we can change in terms of parameters. So, maybe just a guess as to maybe one or two steps. It doesn't have to be in proper sequence or anything. Like, what might be some components I would have used?
Maybe some rotation or scale components.
Okay, there is some rotation and scale components. So it helps me to rotate the flow plates to give a twisted look. And also scaling is involved because you can see the flow plates are of varying sizes. Any idea what's the very first step? There's one more step that you have missed out. Range, move, rotate, loft. Range, yes, we have used it in different places throughout the algorithm. Lofting is, yes, definitely the final step. And move. Move is the very first step we do. So to put all of the things that we have guessed together, first you import the flow plate. As soon as you import the flow plate, I create multiple flow plates. So since we are considering it to be a skyscraper, the very first thing for a skyscraper is to have multiple flow plates and not just one. So I move the flow plates to create the necessary flow plates for the tower. This controls the height as well. So changing the number of flow plates automatically controls what's the total height of the tower. Once we have all the flow plates, I want to apply two kinds of transformation. One is scaling. You can see the size of the flow plates are changing at different positions throughout the tower. Second, you can notice some kind of a twist happening. And since flow plates are 2D, instead of twisting, you just rotate it at different angles. So once I have the flow plates for the skyscraper, I apply the scaling transformation. It makes sure that each flow plate is of a different size. And after I scale it, I rotate the flow plates. It adds some twisted effect to it. So each flow plate is again rotated to a different angle. Once it is done, we create a surface using loft. That's it. So these are the steps involved in recreating this algorithm. Let us try it from scratch. I'm just going to hide the preview. Curve, feel free to create any curve for the plan. You can have a curve done in AutoCAD, which would probably be more precise in case you have like a basic plan and a zoning set, or you can do the same thing in Rhino as well. For now, maybe just try a random shape. I have taken a star-shaped polygon. When you choose polygon, you have a star option inside that. Just select it, give a center, outer radius, and an inner radius. And also, if you notice, the corners are filleted. So to fillet the corners, I'm using the command called as fillet corners. Selecting the curve, enter. Radius, I'm just going to give 1. And you can see the corners are filleted to give a smooth result. That's it. So this is how I created this curve. But feel free to create any other kind of curve or curve of your preference. It's not necessary to have the same thing. I'm going to import this curve using the curve component. Right click, set one curve and selecting this curve. Once I have this curve imported, the very first thing is to have multiple flow plates. To have multiple flow plates, I'm going to move and create copies of this. Geometry I'm moving is the flow plate. The motion in which I want to move is along the Z vector. Now, if I give one single number in Z vector as factor, so if I give maybe 5, gives me one single height. If I give two numbers, let's say 5 and 10, it's going to give me two copies here. So how many of the numbers I'm specifying, that many number of copies I would be getting for the flow plates. And obviously, instead of giving number sliders, I'm obviously going to choose either a series or a range. Let's try the series first, and then we will see how series and range is differing and what is a better option. So I'm going to use a series of numbers. Series is asking me the starting value. For giving the height for the flow plate, what do you think the starting value will make the most sense here?
Zero is okay, right?
I could give it as 0. Essentially, starting value refers to the position of where the first flow plate has to be. First flow plate, if you want it at the ground level, give it at 0. If you want it at a plinth level, give the height of the plinth, maybe 0.3, 0.6, depending on what's the height of the plinth. You can specify that to be the start value. So start refers as to where the first flow plate has to be positioned. I want it at the ground level, so I'm going to give it a 0. What would the step value indicate here?
Flow height.
It will indicate the flow height, that is the differential height between each flow plate. Grasshopper takes the unit of Rhino. So whatever units you're working in Rhino, make sure you give a number according to that. My Rhino unit is meters. So the flow height is going to be 3.5. Let's try 3.5. And plug it in here. And finally, the count, what would it indicate here?
Anything,
Could you repeat?
anything like any number.
I mean, any number, yes, but in this context, what do you think the number indicates in terms of moving
Number
factor?
of floor plates you want to create the height.
Exactly, the total number of flow plates I would like to have. I would like to have maybe 65 flow plates. Let's give that here. Resultant series goes into the factor. And you can see automatically I get multiple flow plates like this. So the very first flow plate is at level 0. That's starting value 0. 3.5 is the differential height between each flow plate. If I increase the 3.5, let's say to 10, you can see that the distance between each flow plate has automatically increased, right? So step value indicates the differential height. And finally, the count is nothing but the number of flow plates I would like to have. Can be 65 or more or less. It's completely up to you. Now, instead of series, I can also use a range. And if I were to use a range, the difference would be the domain. What do you think the domain will indicate for the factor of movement in this example?
Maximum height.
The minimum and the maximum height. So domain is going to be between 0 to the maximum height of the tower, which is 65 by 3.5, I think something close to 200. So it depends on what aspect of the tower you would like to control. If you want to control the differential flow height, that is the step, you would use a series. If you'd like to control the total height of the tower, then you would use the domain in the range and go ahead with the range component. So depending on what aspect you like to control in the tower, choose between a series and a range while you're moving the flow plates. I'm going to use a series because I would prefer to have more control over the flow height here. Once we have the multiple flow plates, we're going to start applying the transformations, which is scaling and rotating. I'm going to start with scale. It's going to help me change the size of each flow plate. Geometry to scale is every single flow plate. I want each flow plate to have a different size. I'm going to connect it here. Center of scaling by default, it goes to the origin. We want it at the center of each flow plate. It makes sense to scale the flow plates within itself. So I'm going to find the centroid for that using area component. We find the center, use that as a center of scaling. At this stage, preferably hide the move component. If you don't do that, you would just be confused a little. So make sure all unnecessary previews are hidden. Now for the scaling factor, default is 0.5. But any number I give, so if it is 1, it retains the same size. And if I scale it to something smaller, you can see the entire tower scales to a smaller size. That is not what I want. I want each flow plate to have a different size. What do you think I should do to achieve that?
And have a range to that.
Exactly, have a range of numbers acting as the factor. Right now, there are 65 flow plates, but there is one single scaling factor. So what happens is because of how data matching works, the same scaling factor applies for every single flow plate. If I had multiple scaling factors, each flow plate gets a different size, which is exactly what we are going to do. We are going to create multiple numbers acting as a scaling factor. Now, what is a better option, a series or a range? What would make more sense here?
A range could work a little bit better because we can control the minimum size and the maximum size of the float plate that way.
Exactly. A range will make more sense here because we are using it for scaling factor. And the minimum and maximum scaling factor, that's the minimum and the maximum flow plate size, is something we can control. If I use a series, I'll have to control the differential size between each flow plate, which is going to be a lot more tricky for me to figure out. Like it will involve a lot of math for me to figure out. So rather than that, I would prefer a range, mainly because range helps you control the minimum and the maximum size of the flow plate. So I'm going to use the range. It's going to ask me for the domain. Domain always refers to the minimum and the maximum of where you're connecting the range. If I'm connecting the range to factor, minimum scaling factor and maximum scaling factor would be the domain start and domain end. Minimum scale factor maybe 0.1. Again, guys, be careful when you're giving numbers here. Make sure it makes sense with the whole algorithm. Scaling factor refers to the flow plate size. 0.1 means 10% of the size I'm having right now. Maximum, I would have 1.5, which is probably 1.5 times the original flow plate I have given here. And as always, it can't be numbers, it has to be a domain. So we construct domain between these two numbers. 0.1 being the start, 1.5 being the end. Resultant domain goes in here. What about the steps? How many, what number do you think I should connect to the steps input here?
65.
65, basically how many ever geometries I'm trying to scale, that many numbers I want in the scaling factor, which becomes the step. Directly connected from the count, it's better than having a separate slider. Why? Because count controls the number of flow plates from the beginning of the algorithm. So I make a change here, we would automatically want the rest of the algorithm to reflect it. So better to connect from the original number slider. If I were to connect this, there would be the same two problems. First being, if I zoom in, last flow plate scales twice. How can I rectify it?
Expression.
Change the expression. Don't forget the step of changing the expression, guys, because I'm pretty sure you would not zoom in and check this. This would just stay as a mistake. Make sure you don't forget it. Always go to expressions and change it to x minus 1. Do not forget it. Soon as I do that, it's rectified. Second is base has to be wider, top has to be narrow. So I'm just flipping the domain start and domain end to give the form that I'm looking for. Again, form is very, very boring. I'm going to add a graph mapper to add some interest. Input of graph mapper connected to range, output where the range was connected. So it always tucks itself in between range and where it used to be connected. Change the two things, which is right click, add a graph type. Let's try sine graph. I'm just going to have something close to the original tower that's on the left hand side of what we're creating right now. And as soon as you add the graph type, the second immediate thing to change is the domain. Range has a domain between 1.5 to 0.1. Graph mapper needs to match that. So double click. X0 is domain start. Let's get 1.5. X1 is 0.1. Again, 1.5 and 0.1. Hit OK. I have a tower like this. Now changing the nodes of it will start giving me a different form. Let's just have a temporary position for now. Once we're done with the tower, we can always change it to make it more interesting. Once the scaling is done, I want to add another transformation. You can see this twisted shape. So I'm going to rotate the flow plates as well, using the rotate component for that. Very first thing I want you to do when you bring the rotate is change the unit of angle. Any component in Grasshopper, if you see an angle, it is always going to be in the unit radians. We are used to working in degrees, so make sure you change it according to that. I'm going to change the unit of angle here by right-clicking and changing it to degrees. As soon as I do that, just look at the mouse. It adds a symbol here. And it explains that the angle inside this parameter are defined in degrees and not in radians anymore. So make sure this is the very first thing to do as soon as you bring rotate. Then it'll ask you the geometry you want to rotate. I want all of the scaled flow plates that I have updated right now to be rotated. And the component has some default inputs. Angle by default is 0.5 pi, which is a very, very minute angle. And the plane is again a default plane starting at the origin. Let's just go to the top viewport. If I were to give a different angle, let's say 120, just to understand how the default values are, you can see that when I give an angle, it rotates about the origin. Why it rotates about the origin is because the plane of rotation, plane is nothing but the base point of rotation. So when you're doing rotate in Rhino or any drafting software, when you type rotate, it will first ask you the object to rotate, which is the same as the geometry, like what geometry you're trying to rotate is what you select, hit enter. Then it will always ask you the center of rotation or base point of rotation. This center or base point of rotation is what you are specifying in plane. Right now, the plane is set to the origin, which is why rotation is happening like this. We want the rotation to happen within the flow plates. So obviously the center is going to act as the plane. As soon as I do that, you can see the rotation makes within the flow plates itself. Now, hiding again every previous step, please do not forget it. If you forget to hide the previous steps, this is what you will see in your screen right now. Even though there's nothing wrong with your algorithm, you will have very weird preview. Hide everything except the final step you're working on. Now, when I give an angle of rotation, you can see the entire tower rotates as though changing the orientation. That is not what I want to have. I want each flow plate to have a different angle, so it gets a twisted profile kind of form. What should I do to achieve that? I repeat the question again. Right now, when I'm giving an angle to rotate, the entire tower rotates. Kind of looks like I'm changing the orientation of the building, which is not what I want to do right now. I want to give a twisted profile to it, meaning each flow plate has to rotate to a different angle in order to get a twisted profile. How can I achieve that here?
Can give a range component and then add a graph mapper.
We once again use the range component graph mapper. We'll see if we need it later, but range is the main component we need here. We have 61 flow plates. Each flow plate needs a different angle, which means I need to give 61 numbers acting as the angle. And once again, range makes more sense because I would like to control the minimum and the maximum angle. If I were to use a series, I would have to control the differential angle between each flow plate, which is again too much of math. If I give the minimum and maximum angle, I can give something like 0 to 360 if I want a complete twist, 0 to 180 if it's like a half circle twist. So it depends how much twist I would like to have. I can control the minimum and the maximum angle, and hence range would make better sense. Domain is the minimum maximum angle, which is 0 to 360 for me. And then using construct domain to have a domain between that. And once again, what do you think I should connect to the steps for the range component? So what would we connect to the input steps of range for giving into the rotate component?
The angle, right?
Could you repeat?
The angle.
Angle, we give it in domain. Domain specifies the minimum and the maximum angle. Steps refer to the number of angles I would like to have, or the number of values that has to come in the output of range.
Number of floors.
Number of floors. So I would just drag, plug it in to the 61, which was initial number of floors. I think this is a good example to explain a relay, which was earlier asked. So when you double click, you get the box. So when I have a relay, it just has more control. Like I can just organize it like this instead of it all going in a congested wire. This is where you normally use relay. This is out of topic, but just to show a better example of what we saw earlier. And again, don't forget to change the expression, because if you do, and you connect it. There are 61 flow plates, but after rotating it becomes 62. And if I zoom in, I would see last flow plate overlapping. So do not forget to change the expression. Make sure you definitely do it without fail. And finally, after you rotate, if you would like to add a graph mapper, you can do that. It just helps you control the amount of rotation. Right now, it evenly rotates from 0 to 360, from the bottom to the top curve. If you would like to have some variation to it, like the twist happens more at the bottom and becomes more straight, or vice versa, then you can add a graph mapper. Let's just use a graph mapper and see how that is between the range and the angle, and the two things, which is graph type by right clicking, and also the domain by double clicking. It's 0 to 360 this time. Again, 0 to 360. Hit OK. Let's play with the graph mapper. You can see it starts to control the kind of twist. Again, let's do one thing. Let's see the final surface by lofting. And then changing these parameters is something way more visual. So let's just change it in here, change it in here. You can see that the kind of twist that's happening is more controlled. And once you're done, start playing with the parameters. You can increase the height of the tower. You can change the form of the tower. I think maybe we can try with a bezier as well. It was looking pretty interesting when I was explaining in the beginning. Yeah, something like this. And playing with the kind of twist that's happening. I have a form that looks something like this. So you can see that the two things that I have tower A and tower B that we just created. They both have the same exact flow plate, but the form of the tower is something entirely different. Similarly, by changing the parameters, you would get again a third completely different option. And you can kind of choose between all of it as to what works best. Now, when you guys are trying it, one of the most interesting thing is you can just have a couple of copies. Let's say changing the parameters is not doing it for you. You feel like still the form is very boring. You can start having different shape for the plant. So maybe let's have one where we use an ellipse like this. And let's maybe have another where we just randomly draft a curve. I'm just going to randomly have a curve, looks something like this. Let's maybe scale it a little, right? And then for each of the algorithm, let's just have a different curve imported. For the second one, let's right click, set one curve, import the ellipse. And for the third one, okay, so let's finish off the ellipse. So let's just change the parameters a little. And also change the way the twist is happening. And I'll have something that looks like this. And for the fourth one, the third one, let's just do right click, set one curve and import it. And let's have a sine curve for this. I think let's something like this. And let's change the way the twist is happening. It gives me an entirely different form this time. Right. And that's it. Again, I haven't changed every single parameter. You can change the total angle of how much the twist is happening, so on and so forth like that. But just by using a couple of different plant curves and changing a few parameters, you can see I have three different entirely, like completely different tower options here. And I'll show you some more examples. So what I want you to do is come up with an interesting plant shape. Any shape except a circle will be interesting with this algorithm. Circle, when you rotate, won't have much of a difference. So anything apart from a circle will make sense for this algorithm. And also some of the interesting shapes I would like to show you is, this is from some of the previous student works. So one interesting example that I liked from one of the previous student works is same exact algorithm, of course, a different plan. Here it looks something like this. And apart from using the different plan curve, in this case, I would say not a plan, but a cross section. You can see that instead of taking it to be a vertical tower along the z-axis, the student has just moved it along the x or y, basically along a horizontal axis. And then when you create the form, it creates an interesting horizontal structure like this. And of course, there is some detailing done where the surface is split into two portions, portion A and portion B, where one portion has one kind of detailing and the second one has some funneling detailing. So we would see the detailing in the next part of the algorithm. But for now, I think the form is interesting on how the participant has attempted to go as a horizontal example. Another interesting example I like by a participant is this one. Again, same exact algorithm, but this time instead of using a curve as a base geometry, the participant has used a grid of boxes. So you start by creating a grid of boxes, you move it to create multiple array of boxes in the z-axis, and then you scale it and you rotate it and you get this kind of form. Obviously, you don't do a loft at the end because you have boxes and not a curve. But use the same algorithm, slightly different initial geometry. Instead of a curve, you use a solid and gives you something really interesting like this. So I think this is also another interesting experiment done by the participant. But apart from participant works, I also found some interesting example of this in just by searching online. So just by searching some skyscraper concepts in Pinterest, I found these interesting examples. This is once again, take a look. It's a very simple basic form, something like this. It's just rectangles with 4 legs. And again, you can see the steps we have used. You can see there are multiple floor plates. You can see varying sizes, which means scaling is done. You can also see a rotation done. There is 90-degree rotated, like this is the initial position. At the last floor plate, it has moved to 90 degrees. So there is also a rotate used here. I don't think they've used a loft. They have just created floor plates with boundary surfaces. And also the detailing is interesting. You can see the floor plates are for the initial moved curves. Initially, when you move, you get the same size floor plates throughout. So that's like the moved curves. And then the loft is done for the final lofted, rotated geometry. So this detailing is also something I found interesting. Another example is this one. Now, any idea how this is done? I want you guys to guess with what we saw right now. Any idea how this can be done? Five polygons. Maybe just do one polygon and then do a polar array. So maybe start with one single polygon. But this time, when you are rotating, the center of rotate is not inside the polygon, but it's going to be outside. You'd probably have the center of rotation somewhere here. And also, if you notice, there is no scaling. All the entire form is having the same size, so no scaling. You just move and rotate it. After rotating, you maybe do an array polar to get 5 copies of it. So this is another interesting example, which I think is a slight variation from the steps we have done. And another interesting form is this one. I think the plan is kind of like a boomerang, but I like the end shape of it. It looks quite interesting when you look at it with this kind of detail. I'll share these references with you in WhatsApp. So why we are discussing this is, I don't want you guys to just do a copy paste of what we just discussed. Try to have an interesting shape for the plan. Try to add some variations to this algorithm. You don't necessarily need to do the same exact thing. It's about 8:50. Let's take 15 minutes for this, and then we will see how to go about detailing this specific tower. Any questions? By the way, I think there was a question in the chat. How did you copy these options? I'm assuming you're asking how to copy the algorithm. Just select Control C, Control V, gives you a copy, move it aside. That's it. And for those of you who want to just run through the flow again, I'll just quickly run through the steps. We start by creating the curve in Rhino and import it. Step 1 is to have multiple flow plates. We do that by using a move component along with series. It gives us multiple flow plates. Once we have multiple flow plates, we start applying the transformations. First one being changing the flow plate size. We do that by scaling. Each flow plate gets a different scaling factor along with a range component and a graph mapper. Second transformation is to rotate. I'm rotating each of the flow plate at a different angle by using another range and graph mapper. Remember to change the angle to degrees. You right click and change it to degrees. Once you have the desired flow plates, just loft it, you will get the final tower. So in terms of primary steps, you have the flow plate imported. You move it to create multiple flow plates, scale it to give varying sizes, rotate it for varying angles, and then loft it. Definitely you'll be using range and graph mapper every now and then whenever you need like multiple numbers to be generated. But the key steps in the algorithm is multiple flow plates, scaling, rotating, and then lofting. That's it. Try it out. It's about 8:50. And then maybe 15 minutes by 9:05, we will continue with the detailing part of it. Any questions? You can go ahead right now. I'll just pause the recording to practice. Okay. Let's pay attention. Moving on to the detailing part of this example. So you can see that I have done some additional details to this algorithm. I haven't just left it as it is, like I haven't just left the tower as it is. You can see I have some details added to the form. And in this case, the detail I have added is, you can see that from the entire tower, I just have a portion of the surface. So instead of having the entire surface, I just have a portion of the surface. That is the first detail. Second detail is the flow plates are having a surface and extruded. So it has an exposed balcony kind of finish to it. So these are the two things I am going to be doing here as well. One, okay, let's start with the surface. Okay, so instead of having this entire surface, I would just like to have a portion of it. If it were in Rhino, how would you go about doing that detail? So you have a surface. Instead of having the entire surface, you just want a portion of it. Then what would you do in Rhino?
Split.
You would do a split. And how would you do a split? Like you would need two things. One is the object to split. We have the tower. It is the object to split. You also need a cutting curve for that. How would you get a cutting curve in Rhino to do a split?
We can create a new one.
Can create a new one. Okay, but don't you think it would be very tricky to create a curve from scratch that follows like this twisted profile of the surface? Any easy way to get a curve on the surface?
And extract the isocurve. Maybe.
Exactly, you would extract an isocurve. And when you extract that isocurve, you can directly use that as the cutting curve for splitting. Same exact thing in Grasshopper as well. So what I'm going to do is I'm going to start by extracting an isocurve. Let's take the middle tower for detailing. The left one, we've already seen it we can see it on the left. So the middle one, which is there done using ellipse, I'm going to consider this. To extract an isocurve, there's a component called as isocurve in Grasshopper. Most of the Rhino functions or most of the Rhino commands would be available in Grasshopper as a component itself. Similarly, we have isocurve asking us for what surface we want to pick the isocurve from. I want it from the lofted surface, so I'm plugging it in. Then it would ask me what is the UV point or which is the UV point from where the isocurve has to be extracted. UV point, we have seen briefly in the previous class. We know that you can't connect an XYZ coordinate. We connect it using the MD slider. Same thing I'm going to repeat here. And when I connect it to an MD slider, you can see the component automatically picks the point on the MD slider and gives us two isocurves, a curve in the U and the V direction. Now, let's say I want the curve at a different position on the surface. I can try moving the MD slider. When I move the MD slider, you can see there is a change in the position on the surface, but the position of the isocurve is varying very, very slightly. Any idea what I would probably have to do? If I want MD slider to pick an isocurve anywhere on the surface or pick a point anywhere on the surface.
Reparameterize.
Exactly.
Reparameterize.
Reparameterize the surface. As soon as I reparameterize the surface, MD slider would pick a point anywhere on the surface to act as UV point, and which will in turn give me an isocurve here. And let's just randomly have it at one position. We can change it later. We have two outputs, that is two output isocurves. So one is the U and the other is the V. I'm just going to connect it to a curve component and see which is which. U curve is a longitudinal one. That's what I'll be using. V curve is a horizontal one. I do not need that. I'm just going to use the U isocurve. Let's hide this one. Now the main purpose is to split. I want to split the lofted surface. The component that is going to do in Grasshopper is called as surface split. This one. It'll ask me what is the surface I'm trying to split. I'm trying to split the lofted surface. So let's connect it here. It'll ask me what is the cutting curve to split the surface. It would be the isocurve we have extracted. Let us plug it in. As soon as I do that, the split has worked well, because when I connect the output to a panel, you can see it gives me two fragments. Even though when I select the component, both the fragment will get selected. So I don't visually see any clear indication. If I look at the panel, you can see that the initial input surface had only one value, which means only one surface was given to split. After splitting, two individual fragments have come. Any idea how to see each of the fragments separately? Like right now, when I select the component, both fragments are selected. I want to select and view only one fragment at a time.
List item.
I can do a list item. So let's just do a list item. List I want to select from is from the list of fragments. Index number by default is 0. Gives us this tiny fragment. Again, for a better preview, hide everything. And you can see that list item with default index 0 gives us this. If I move this and pick up index 1, I would have this one like this. Let's maybe hide one fragment for a minute. If you want to split it at a different position now, play with the MD slider. So playing with the MD slider now will give you a clear idea of, where exactly you would like to split your tower. I think I like to split somewhere like this. Yeah, gives a more twisted shape. And once you have decided on where to split, just have one of the fragments visible. If you do not want to see both of them, just select and see one fragment. And once that is also done, I would like to have the flow plates exposed. Any idea how you would go about creating a surface and adding thickness to these flow plates in Rhino? So these are the flow plate curves. If you were to do these details in Rhino, what would you do?
Boundary surface.
You can do a boundary surface, that is a planar surface. It will create some surfaces here. To add thickness, we can just do an extrusion. It's a planar surface. When extrude will help us add thickness to it. Direction along the Z vector. Factor by default is 1. I think it's too much. I mean, more sensibly, you would probably just have your flow plate thickness. So I'm just going to reduce it to maybe 0.25 and plug it in here and have something like this. So this way you can start adding details and then give a custom preview. So let's plug it in. Let's have a solid color swatch and give a different hue. More desaturated tone. Hit accept. Another copy of the same for the list item. And let's give a grayish preview to it. Again, hiding everything unnecessary. I'll have something like this. Now I'd like to have the tower surface to have some thickness to it. So to add thickness to the surface of the tower, I'm just going to use an offset surface. To make sure it's a proper solid, I would suggest that you have a pufferfish plugin installed. It will give you an offset surface component, which makes it like a proper solid. Surface I would like to offset is this one. And the distance of offset is the thickness of it. Default is 1 units. So if I orbit and see close, I think it's a little too much. Let's reduce it to 0.5. And in case you would like to have both sides offsetted. Right now it's set to false. You can change it to true by using this Boolean toggle. So if you change it to true, you would notice the offset happens on both the sides here. If it is set to false, which is the default, happens on one side. I'll just leave it at the default. And the offsetted one, let's give this the custom preview. And this would be the final tower that's there. That's it. So this way you can start adding details to your surface depending on what kind of detail you have in mind. Doesn't have to be exactly what I did, but the overall idea what I want you to have is it's going to be quite similar to how you do details in Rhino. Like you want a surface, you do a planar surface for the flow plates. You want a portion of a surface, you would split it. And similarly, whatever details you're trying to attempt, it would most likely be quite similar to how Rhino works. But in case you're not able to figure it out, just let me know. I'll help you how you can go about the detailing you have in mind. Any questions? There's one more thing I want to show you, which is how to extract the flow plates. But any questions before we go ahead with that? I'll just wait for a minute to see, or like a couple of seconds to see if there are any questions. Okay. So the next thing we are going to do is we are going to extract the flow plates from the tower and place it out like this. So when you have a workflow as what we are doing right now, you start with the flow plate outline in Rhino or AutoCAD, depending on whichever is your drafting tool that you fix upon. And once you have the basic outline of the flow plate, you start evolving the entire tower, the detailing, like you focus more on the form aspect of the design. And after you're done with the form, you would then get back to the process of detailing the flow plates that would match the final form you have. So in that case, what you would need to do is you would need to extract every single flow plate from the tower and place it on a flat sheet like this. Once you have these flow plates here, you can always bake it in Rhino and start adding more details. So once it's baked in Rhino, you can add details in Rhino or you can draft the details in AutoCAD. But any drafting software, you would continue detailing the flow plates after that. So we are going to create an extraction drawing as what you're seeing in my screen right now. We have a rectangular grid that is going to be equal to the number of flow plates. So how many flow plates are there? We're going to make sure we have that many cells in the rectangle or that many rectangles are created. Each flow plate is moved from the tower, placed inside the rectangular cell. And if I zoom out, you would see that how many of our flows are there? That many cells along with the flows are positioned. And finally, there's also a lettering system which helps us identify which curve is indicating which flow plate. So we have flow 0, flow 1, flow 2, a lettering or a text system that helps us clearly annotate which curve refers to which flow in here. So let us switch to perspective. Let us try it out from scratch on how to go about this. There's a small mistake in this one. You can see the last portion has an additional text. It's something to do with data matching, I think, the algorithm. But when we are recreating it now, I'll just make sure that error is also sorted out. So let us try from scratch. I'll just hide this. I'm going to do for the same elliptical tower that we are seeing right now. And first step, okay, let me just have the elliptical tower in the side and also have the flow plates aside. Okay, so this is the component that is having all the flow plates, and this is what we are trying to extract. The very first thing is we create a rectangular grid. I'm using a rectangular component for that. This is what we used in the previous weekend for the attractor point algorithm. Same thing I'm going to use here. There are two things to consider when you create a rectangular grid while you're placing the flow plates. First thing is you need to make sure the size of the cell is big enough to accommodate the flow plate. Right now, the cell size is too small. It's a 1 by 2 size. And definitely the flow plates cannot be placed inside such a small cell. So I'm just going to increase it to a size. I think the length, if I increase the grid in Rhino, the grid background, you can do it by using the grid command. Let's just increase it to 500. You can see that the length is about this much, which is almost like 25, let's say 30 maximum. The width is about 20, 40, 60. So let's say 30 by 60, a grid size would make sense. I'm just measuring it by looking at the background grid. The dark line indicates 10 units. The light line indicates 1 unit. So depending on that, I'm just approximately calculating. So I'm planning a cell size of 30 by 60 should be good enough. I think a 25 itself should do. Let's have it at 25 for now. And this one, maybe let's have it at 55. In case it doesn't fit, we can increase it later. So the first thing to ensure in the grid is cell size are big enough. Second thing to ensure is the number of cells. The number of cells should be equivalent to the number of flow plates we are placing. So if I have 67 flow plates, I need to make sure I exactly have 67 cells for placing the flow plates. If I have more or less, there's going to be a mismatch in data, which we do not want to have. So what I'm going to do is extend X. I'm going to give it as 67, how much ever geometry is there, which we can drag and plug it in here. So the count tells us the number of flow plates. And extend Y, I'm going to give it as 1. So a grid which is 67 into 1 is definitely going to have 67 cells. That's it. So that's the next thing to consider. Once we have the grid, the second thing to do is to move the flow plates from the skyscraper to the center of the cells. And to move, I'm using a move component, obviously. The geometry to move would be the flow plates. I'm just going to drag the geometry from here and place it. When I switch to perspective, you would see how the geometry moves. By default, the motion is Z vector. Any vector you give, like X, Y, Z, any motion you give along with the factor, let's just give a factor of 45 to see how it works. It is going to move the entire tower as you're seeing in my Rhino screen. It does not move tower to the cell. It does not do that. When you give a vector like unit X, Y, Z, or even the normal vector, it's just going to move all the flow plates in a single direction. We do not want that. What we want is, let's just hide all unnecessary previews. Let's hide this and this. What we exactly want to do here is, I want each flow plate to move to the center of each cell we have created. So how the vector should be is, from here till here should be the first vector. From here to here should be the second vector. So basically from the flow plate to the center of the cell is how I would like to move. When you want to move from a base point to a target point, like how you do using a move command in Rhino or AutoCAD, you have a base point and a target point. When you have a similar situation in Grasshopper, where you're trying to move from a base point, which is the center of the flow plate, to a target position, which is the center of the cell, you would instead create a vector between the base and the target point using this new component called as vector to PT. It's a new component, something you would find really helpful in situations where you want to have a custom vector. It creates a vector between the base point that we would like to have while moving, base point being the center of the tower, target being the center of the cell. So from when you want to move from a base to a target point, or when you want to have a vector between two individual points, use the vector to point component. It will have two inputs. So if you have a vector like this, start of the vector is point A, end of the vector is point B. The start of the vector is the center of the cell, that's the base point. Let's find area and connect the center of the cell. And end point, that is the target position, being the center of the cells here. So I'm just going to find the center of these cells, give it as the target point. And after I do that, I'm just going to remove this unit X. Instead of giving some random unit X, unit Y vector, I'm just going to connect it through the vector to PT component. When I do that, I have this multiple overlapping flow plates, which is when I realize that, it's not big enough. Let's make it a little bit bigger. Okay. So after I have moved it, instead of moving one flow plate per cell, all flow plates are moved to every single cell. Any idea why this is happening? This is a problem we have seen in the previous classes. Any idea, or can you identify what exactly the problem is?
I think we should try list item.
Nope, it's not to do with the list item, it's something else.
I think it has something to do with the tree.
Exactly. Look at the data structures. You can see that there are components that is involving a list and a tree. We had a similar issue in the previous class when you have two different data structures coming together in a component, and you notice this kind of additional outputs. It means it is something to do with the data structure. Like you have additional outputs or you have wrong overlapping chaotic outputs along with inputs of different data structures. Most likely data structure is the issue. Here we have two components with that same problem. Vector to point also has a list entry. Move also has a list entry. You can either just go with a hunch, always sort out the initial component where the problem is happening. So that would most likely sort out the issue. But if you want to know exactly where the problem is happening, like you want to identify it, I would suggest you to retrace the steps. Move component is giving you a visual, clear, wrong output. Look at the inputs of it. Number of geometries I'm moving is 67, which is correct. Number of motion I'm having is 4,489, which means the motion input is having some problem. If I retrace it back, vector output is 4,489, which is wrong. But the number of inputs in point A is 67, which is correct. That is the number of start points. And number of input in point B 67, which is also correct. Vector to point has correct set of inputs, but the output we have is wrong, which means this is where the problem is starting. Flatten it here or graft it, both of it will work perfectly fine. Just do either one of it and it should be sorted. That's it. So as I said, when you see this problem in multiple components, you can either go with a hunch and sort out the first component where you notice two different data structures, or you can retrace the steps from the last, go back, go back, go back. If there are multiple components, retrace and see which component has created that additional number of outputs. So here it's, if I flatten it in the centroid, this one automatically is sorted. And now if I look at the number of moved flow plates, it's 67. I zoom out, each cell has gotten one single flow plate. That's it, it's properly set. Last thing I would like to do is have a text system. Whenever you are producing a fabrication drawing, not only for the flow plates, but when we see fabrication drawing, which would be in tomorrow's classes, generally when you have fabrication data as a fabrication drawings for parametric design, you tend to definitely have a naming or a text system, helps you to identify each module where it is. Here it is the flow plates. We're going to have a text system using the text tag component. There are two components with similar names. There is text tag and there is text tag 3D. They are very similar except for the size input. Text tag 3D gives a size. Text tag does not allow you to specify a size. Oh, I would suggest you go for text tag 3D simply for that reason. Let's remove this. It will ask you at which location you would like to have the text. Let's start with a very basic text and then let's start changing the inputs to make it more detailed or more precise. So for the basic one, location refers to the point at which you would like to have the text. I like to have at the center of each cell. Let's connect the centroid here. The text I would like to have is just a series of numbers, 0, 1, 2, 3, 4, just a basic set of numbers. Let's create it through series. Default start is 0, default step is 1, which works fine. It goes 0, 1, 2, 3 like that. Count is 10. I want a text for each flow plate, so the count has to be 67 on the number of flows. Let's start from here and plug it in here. Another area where a relay will make sense if you would like to organize. And let's connect the text. as soon as you give these two inputs itself, you should see something. Like as when you zoom in or zoom out, you might see something like this. Default size is 1, which corresponds to the units you work in Rhino. Rhino unit is meters. So 1 units means it's exactly one grid size here. I'm just going to increase it to maybe 3. So it's big enough. Even if I zoom out, it's clearly visible. Let's hide the centroid as well. So yeah, I have the text clearly visible. The color is going to be a color swatch, like how we do for custom preview. Let's plug it in. Let's drag the color to black. And finally, justification is the alignment of the text. It's kind of like a Word document. You have align left, align right, justify. Justification is like that. Happens around the location. So right now the location is the center point and the default justification is bottom left. If I right click, you will get a lot of other options. So if I choose bottom right, the point would be at the bottom right. If I choose top left, point will be at the top left. So your justification happens around the point that you have. Let's just choose middle center. So it's perfectly at the center. That's it. So those are the inputs you give. Location is the point where you would like to have the text. Text is the text itself. Size is the font size. Color through color swatch. Justification is right click and specify. This is how you go about working basically through this component. I want to make a few changes here. First is I want to change the text. Having a text like 0, 1, 2, 3 in ascending order, you can see it through point list itself, not necessary to have a text tag 3D. So I'm just going to change the text a little bit more so it makes sense to even have this component. I'm going to add a prefix to the text. If you want to add a prefix or a suffix to a text, use this component called as concatenate. Concatenate combines two fragments of text. So whatever numbers you're having as a series, you can add a prefix or a suffix to it. I'm going to give a prefix through fragment A, and the prefix is going to be floor. You can type this in a panel. You just create a simple panel and then you type floor and you can connect it as the fragment A. Fragment B being the series of text. Look at the result. It gives you floor 0, floor 1 like this. If this is the text connected to text tag 3D, I'll have it written something like this. I think font size is too big. Let's reduce it to 2. The second thing I want to have is the floor in itself. Like, look at the text. It's not having a space. I would prefer to have floor, a small space, and then 0. Again, floor, a small space, and then the number 1, so on like that. And just add it as a character, double click, floor space. If it becomes a character in the prefix fragment A, automatically it affects here. So whenever you would like to have a prefix or a suffix to a bunch of numbers, go ahead with concatenate. Another thing I want to do is when I have text in the center that is this big, sometimes it starts overlapping with the flow plate itself. Like the flow plate itself in certain areas is smaller than that. So if I want to avoid this overlap, what I'm thinking is instead of having text in the center, I would like to have text in the corner of each cell. Any idea how I can achieve that? Like what I need to change in the text tag 3D component in order to have a text starting at the corner of each cell?
Select the vertex.
Select the vertex exactly. So right now I have given the location of the text to be the center of the cell. Instead of the center of the cell, I can give it at the vertex. For cells, if I want to extract the vertex, use explode. It's a curve, which is why it's explode. If it was a surface, it would have been deconstructed. Gives us the line segments and vertices. I want the vertices. Again, vertices would be a list of 4 vertices for each cell. I'm just going to do a list item and list 1 vertex per cell. So when I select, you can see it's just 1 corner vertex. And this one goes into the location. And also let's just bring it closer to the algorithm in here and maybe here. And let's also move all of these a little bit lower. All right, take a look. I have overlapping text. Any idea why this is happening?
Is it taking the grid box cells from both?
Nope. It's again a very common error. We have seen it just a little while ago.
Flatten.
Exactly, flatten. Look at the inputs. It's a tree and a list. So we just need to flatten it. As soon as I do that, it's rectified. So I have 67 location with 67 ticks. Data matching is proper because both are of same data structure. Now that it's in the corner, I would prefer to have a different justification. I'm just going to give bottom left and I'll have something like this. That's it. Hide unnecessary previews. We have the lettering system we are looking for. That's it. Try it out. So we have done two things. We have added, like we have extracted the flow plates and we have done some detailing. Try this out. But before we do that, yeah.
And what if you want to offset that text?
Meaning you want to move this a little?
Yes, like it should not be on the edge.
Any suggestions how we can do that? Anyone? I'm not going to use something like a new component. It's just a logic we would probably do with what we have seen till now. Any suggestions, anyone? The question was how we can have the text a little bit away rather than having it perfectly touching the corner, a little away.
But just put enter, like in that text.
Actually, yes, that is a smart suggestion. I wasn't thinking of that. I was thinking of something else. What I was thinking is you change the location. Instead of having the location at the vertex directly, you can maybe move it a bit using the move component. And move it along the X vector. If you would like to move it in both X and Y, so right now when I'm moving it in X, it's exactly how floor 6 is moved by space. Maybe move could give this advantage of moving in two vectors simultaneously. If you want to move in two vectors, like along the X, Y, Z, if you want to move in two vectors simultaneously, X and Y, you can use vector X, Y, Z. Along X, let's say I'm moving for 1 units. Along Y, let's say I'm moving for 0.5. You can see that the point that is there, maybe let's just move for 1 for the visual sake. You can see the point moves for 1 units along the X vector and 1 units along the Y vector. And if you want, you can add a Z to it as well. And then using this as the location for the text, it moves to that position. So now maybe you don't need a space character, but I think the space is a really different suggestion I wasn't looking for. And guys, just give me a second. Someone is ringing the doorbell. I'll be back in a second, just a minute. Okay, guys, I'm back. So any questions? That's it with this portion of the teaching. So any questions? Okay, so before we take a practice break, I just wanted to ask a quick question. It's about 9:45 right now. There's another teaching portion which would span about 45 minutes. Would you guys like to have today's class extended? So maybe let's say practice of 10 minutes and another teaching of 45. It would probably take another hour, so maybe till 10:45. Would you like to extend it till then? Or would you prefer to have tomorrow's class a tad bit earlier? Maybe we would start at 5 o'clock instead of 5:30. Can you please let me know what works best for you? Just type it out in the chat. I would personally prefer tomorrow a little earlier, but it's up to you guys. We'll just take a collective decision. Okay, great. Everyone also prefers tomorrow. Okay, so we'll have tomorrow's class at 5 o'clock. I'll put a message in the group as well in case for those who have missed today's session. And maybe we'll wind up with the session. The practice, you can just try it out after class. The recording will be uploaded in another half an hour to 1 hour. And yep, that's it for today's class.